So in this video, I will be deriving the equations that represent the change in pressure and temperature with altitude, assuming that the decrease in air temperature can be modeled by an adiabatic reversible expansion. So in this problem, we are thinking about some kind of air bubble at a low altitude, z equals 0. And then as we increase our altitude, this is going to expand. Like if we increase to 1,000 meters, this would expand to a larger balloon. And so we're going to be starting with the static equation, or the fluid statics equation, and kind of going from there to derive these two expressions. So our fluid static equation is the derivative of pressure with respect to height going to be equal to the density of the fluid times the acceleration. In this problem, since we defined that our height is positive upward, and we're using the acceleration due to gravity, that is going to be negative. So this expression is going to be equal to negative rho g. And then from here, we can use the definition of density to rewrite this in terms of gas law equations. So we're going to start with density. It's going to be equal to mass over volume. Mass is going to be equal to the number of moles times the molar mass, and then over volume. We can rewrite moles using our gas laws as RT as PV over RT, and plug that into the equation. So our new equation is going to be negative PMG over RT. Notice the volume variables cancel, so we're just left with just this. Now from here, since we are assuming an ideal gas, the first law of thermodynamics apply, and we can use that with the adiabatic reversible expansion to start to derive our expression. So the first law of thermodynamics is the change in internal energy is equal to a small amount of heat added plus minus P dV. So in this case, since it's an ideal gas, the change in internal energy only depends on temperature. We're going to rewrite that as CV dt equals Q is equal to 0 because it's an adiabatic reversible expansion, and we're just left with pressure times volume. Now we can use gas laws again to rewrite pressure. So P is going to be equal to RT over V. And now from here, we can separate our variables and integrate. So I'm going to divide R and T over to the left side of the equation, which leaves us with CV over R times dt over T equals negative dV over V. From here, we can integrate both sides and then set our bounds of integration. So the lower bounds are going to correspond to this lower altitude. So V1 is going to be the volume at our lower altitude. T1 is going to be the volume at the lower altitude, or going to be the temperature at the lower altitude. And then for our upper bound, it's going to be the volume of the altitude we're going to. In this case, it's 1,000 meters for my example. And then same thing with temperature, it's the temperature we're going to. I'm going to create these into dummy variables of integration so that we don't get them confused, and then integrate. So basically these are just integrating 1 over x, which just gives natural log. So for the left side, we still have our constants, CV over R out front, times the natural log of T1 over T equals the negative, because we have the negative sign out front, natural log of V1 over V. Using logarithm rules, we can cancel these out. So the terms out front will become the exponents. So this will be raised to the CV over R. This will be raised to the -1. and the logarithms will cancel. So we're left with T1 over T to the CV over R equals V over V1. And then from here, I'm going to use the ideal gas law again to rewrite our volumes. And so volume is going to be equal to RT over P. And so this is going to be equal to RT over P over RT1 over P1. These R's are going to cancel, and we're going to be left with P1 over P times T over T1. And then from here, I'm going to multiply both sides of the equation by T over T1 in order to get rid of this term. So I'm just going to multiply this, T over T1. And on the left side, since we're multiplying by, I'm multiplying by T1 over T to get rid of this term. And then on the left side, since it's just the same term multiplied, the exponent is just going to be CV over R plus 1. This is going to cancel out. So our new equation is, I'm going to write it over here, T1 over T to the CV over R plus 1 equals P1 over P. So now using something we learned from MEB last year, we can rewrite this exponent. So CV plus R is equal to CP. So if we rewrite this with a common denominator, you get CV plus R over R. So as you can see, this is just CP. So this exponent just becomes CP over R. And now from here, I'm just going to solve for T, and then we'll be able to plug it back into our static fluid equation and get the expression for pressure as it changes with altitude. So I'm going to solve this and actually write it off to the side because we'll need it later. I made a mistake. I just realized that I wrote this backwards. So this is actually T over T1. T over T1. I just flipped these when I did my integration. I also flipped these on accident. This is going to be T1 over T. And so we are multiplying by T over T1. And so all that really does is just flip this to T over T1. But now from here, we can solve for T. So the right side of the equation, to get rid of this exponent, we need to take the root, the CP over R root of this side. So it's just going to be P1 over P to the CP to the R over CP. And then, so this is gone. Now we're just left with T1 in the denominator. So we're going to multiply by it, and T1 equals T. Let me just double check that I didn't make the same mistake here. I think I did. So again, with the integration, I accidentally wrote V1 over V when it should be V over V1. So all that really changes is our end product here. This is just going to be P over P1. And same thing over here, P over P1. Good thing I caught that. We would have ran into problems later on. But now I'm going to erase this, and we'll plug this expression into here and get the expression for pressure change with respect to altitude. So once we plug this into here, on the left side of the equation, we have dP over dz equals mg over RT, or mg over R is going to be pulled out. And then we have T1 in the denominator. And then we are dividing the pressure by the pressure to R over Cp. So what that gives is just P to the 1 minus R over Cp times P1 to the Cp over R. Right. I think this is just R over Cp. This is just going to be R over Cp. Because you divide by P1 to the R over Cp, it's in the denominator, so it'll be flipped to the numerator, so that is our expression. From here, we can separate variables and integrate. So, kind of similar to last time. I'm going to multiply this to the other side, divide this term to the left side, and then these terms are constant, so I'm just going to leave them on the right side of the equation. So for the right side, it's just our constant terms. And dz, and then on the left side, we divide this over, so it just becomes P to the R over Cp minus 1 times dP. And then from here, we can integrate both sides and set our bounds of integration again. So we have our starting altitude of Z1 and the altitude that we're going to. Again, making this a dummy variable so we don't get it confused. And then same thing on this side, make these dummy variables of integration. And we have P1, which is the pressure at the starting altitude, and then P, which is the pressure at the altitude that we're increasing to. From here, we can integrate. So I'm going to do the right side first since it's a little easier. Actually, I'm going to plug in my laptop because it's about to die. Make sure we're still recording. We're good. All right. Now I'm going to take the integrate the right side. And so that's just going to be all of our constants out front. And then the integration of dz is just c. So it's going to be z minus z1. And then doing the left side, we add 1 to the exponent and then divide. So it is going to be pressure times R over Cp, and then we need to divide, so it's going to be Cp over R. And this is evaluated from P1 to P. And so now I'm going to plug these bounds into the left side of the equation, and then divide by Cp over R. So when we divide by Cp over R, these R's are going to cancel out, and we just get negative mg over Cp times T1 times P1 to the R over Cp times Z minus Z1. And then for the left side, this is gone because we divided it over. So it is P to the R over Cp minus P1 to the R over Cp. I'm going to add this term to the right side of the equation. And as you can see, we now have two like terms, so I'm going to factor it out. So this first term, this term is 1, and then minus this term, which is just mg over Cp, the temperature at the starting altitude, times Z minus Z1. That looks good. And then we're just left with P R over Cp on this side. To get rid of this exponent, we need to take the R over Cp root. So that is just going to cancel out here. And we'll get pressure alone. Cp over R. All right, I'm going to erase everything except for this bottom expression. And this is the expression for the change in pressure with respect to altitude. So now we're going to use this to get the equation for temperature. So how we're going to do it here is we're going to plug this equation that we just got for P over here. So this equation that we derived earlier is coming back. So we're going to plug that in, still just T on the left side times T1 the P1s are going to cancel out, and we are going to be left with this raised to the R over Cp. So then it's just going to be 1 minus mg over Cp T1 times C minus C1, and then these exponents are going to cancel each other out. So this is the expression for the change in temperature with respect to altitude, and then again, this is the expression for the change in pressure with respect to altitude.